The effectiveness of a RAG system depends largely on the quality of the context it receives at runtime, which in practice is driven by how data is chunked and how context window is managed. You can have a powerful embedding model, a fast vector database, a large context LLM, but if chunking is wrong, retrieval becomes noisy, the context gets diluted, and the models still produce incorrect or incomplete answers. Welcome back to the channel. If you are new here, this channel focuses on applied AI engineering, RAG systems, and real-world LLM architecture in practice. In this RAG series, we started by covering the basic RAG pipeline, where we covered how chunking, embeddings, vector databases, retrieval, and generation work together. Then we moved into advanced retrieval techniques that help provide better context to the LLM. In this video, we are going to zoom into two critical components that directly affect answer quality. These are chunking strategies and context window management. To understand why chunking matters so much, we first need to be clear about what chunking actually means in context of RAG systems. Chunking is not just splitting documents into small pieces. It is the process of converting raw data into retrievable units of meaning. A good chunk should represent a complete idea, be understandable on its own, fit efficiently into the model's context window. LLM understands only tokens. Chunking is how we decide which tokens the model is allowed to see. Once we understand what a chunk represents, the next question becomes how much of that information the model can actually see at once. And that brings us to the context windows. A context window is the total number of tokens the model can process in a single request. This includes the system prompt, instructions, retrieved chunks, and the model's own generated output. This means that a 120K context model doesn't give you 120K tokens for retrieval. You must budget for everything. In practice, only about 60 to 75% of the context window is safely usable for retrieved content. Bigger context windows are helpful, but they do not eliminate the need for good chunking. Sometimes more context simply means more room to make mistakes if retrieval is noisy. Having a larger context window sounds appealing, but in practice, it introduces its own set of trade-offs. In reality, more tokens increase cost, more retrieved chunks increase distraction, and it may increase repetitive information across chunks, and more context increases the chance of irrelevant information influencing the answer. Therefore, choosing right chunk size is one of the most important design decisions in RAG. Let's look at some trade-offs. If chunks are too small, it loses semantic meaning, requires many chunks to answer a single question, and forces the model to reconstruct logic on its own. If chunks are too large, it produces diluted embeddings, retrieve irrelevant information, and waste valuable context space. Okay, so let's look at some of the chunking methods. The first one is fixed size chunking. It's a simple text processing method that splits documents into uniform segments, which are of a predetermined length, characters or tokens. They are often with an overlap. This chunking in particular is attractive because it's simple, predictable, and relatively inexpensive to maintain. It doesn't require deep pre-processing, it scales really well, and it's easy to reason about from a cost and infrastructure perspective. For many use cases, especially smaller datasets or early prototypes, fixed chunking is often sufficient. However, as RAG systems move into production and are applied to larger and more complex datasets, the limitation of fixed chunking become more visible. Cutting text purely by token count can break semantic meaning, split related ideas across multiple chunks, and ultimately degrade the quality of the context provided to the model. The next method is sentence-based chunking. It's a text processing method that divides large documents into smaller segments by splitting them at sentence boundaries, ensuring each chunk contains one or more complete sentences to preserve semantic meaning and context for NLP tasks. While fixed chunking is operationally convenient, it doesn't optimize for how large language models actually reason over information. This is where some more advanced chunking strategies come into play. These techniques are designed to improve the quality, coherence, and relevance of the context that is retrieved at runtime, which directly impacts the accuracy and the reliability of RAG responses. One such approach is structural chunking. Structural chunking leverages the inherent structure of a document rather than treating it as flat block of text. Many documents already encode meaning through headings, sections, lists, and paragraphs. By aligning chunks with this structure, we preserve logical groupings that humans naturally use when reading and searching for the information. For example, in a technical document with a section titled Authentication and Authorization, Grouping all related paragraphs under that heading in a single chunk ensure that when a user asks about authentication, the retrieved context contains a complete and coherent explanation rather than a fragmented subset of it. If a section is too large to fit within a token budget, it can then be subdivided further while still respecting the original structure. This approach works particularly well for technical documentations and the policy manuals and the texts. Building such structural chunking, we can go a step further with semantic chunking. Semantic chunking focuses on meaning rather than layout or sentence boundaries. Instead of assuming that proximity in a document implies relatedness, semantic chunking groups text based on conceptual similarities. In practice, this often involves embedding smaller units of text, such as sentences or short paragraphs, and clustering them based on semantic similarities. This is especially useful for documents that are poorly structured or that frequently switch topics. For example, consider a policy document that alternates between compliance requirements, billing rules, and security guidelines. Sentence-based chunking might mix these topics together, but semantic chunking can group all the billing-related content into one coherent chunk, even if it appears in multiple places throughout the document. The result is more focused retrieval and higher quality context, although it comes at the cost of additional pre-processing and computational overhead. Another advanced approach is language model-based chunking. In this strategy, a language model itself is used to determine chunk boundaries. Rather than relying on predefined rules, we ask the model to identify logical breaks, topic shifts, or coherent passages within the text. This is particularly valuable for unstructured data such as meeting transcripts, customer support conversation, or any free-form notes, where traditional structures are missing or unreliable. For example, a long meeting transcript may contain multiple agenda items discussed in a sequence. An LLM can identify where one topic ends and another begins, grouping related exchanges into meaningful chunks that reflect how the conversation actually unfolded. While this approach is highly flexible and often produces excellent semantic coherence, this is also more expensive and less deterministic, making it best suited for targeted use cases rather than as a default strategy. In practice, most production-grade RAG systems do not rely on single chunking method. Instead, they use hybrid chunking strategies that combine multiple approaches. A common pattern is to start with fixed size chunking and then move to structural chunking to respect document layout, apply dynamic token-based limits to stay within context constraints, and optionally refine chunks using semantic or language model-based techniques where higher precision is required. This layered approach balances cost, scalability, and retrieval quality while remaining adaptable to different types of data. The key takeaway here is that while fixed chunking is easy to implement and maintain, it optimizes primarily for operational simplicity rather than reasoning quality. Advanced chunking techniques exist to bridge that gap. By aligning chunks more closely with meaning, structure, and intent, we provide language models with cleaner, more relevant context, which in turn lead to accurate and reliable RAG responses. Okay, let's see those chunking strategies we discussed implemented in Python code. I start by importing some standard libraries, which are OS for environment variables, RE for simple text splitting, JSON, and NumPy for scikit-learn, because scikit-learn uses arrays, and this is to do maths on that. Then I import tick token. This is for token counts. And then I import Groq for API client and for using LLM. And then I use TF-ID vectorizer and cosine similarities for from scikit-learn kit for semantic grouping. Next is here I defined the model name that I'm going to use, which is Llama 3.1 8 billion, because it's fast and I can swap it by setting the environment variable. Next, I create the tokenizer using tick token. This matters because the chunk sizes and context windows are token based, not character based, so we need something to count the tokens. I define token length function as a helper function to return the token length for any string that we pass. Decode token function converts the token array back into the text. The next one is clean WS, just to normalize the white spaces so the chunk previews look neat on screen. Then I define a small document with heading and paragraphs. Then I define one question, which is what are the trade-offs of overlap in RAG chunking. Okay, next I am implementing fixed size chunking. This is the simplest possible method. Tokenize the whole document, the whole text, and then cut every n tokens. So I encode the whole the whole text to tokens. Then I loop through it in the steps of chunk size. Each chunk is just a slice of token, which is then decoded back into text. This approach is simple and predictable because we know the chunk sizes, but it can cut mid-sentences and break meaning. Next function is the same fixed size chunking, but with overlap. We are adding an overlap in between the sentences, in between the chunks. I first validate here whether the overlap is smaller than the chunk size. Then I encode the whole text. And then here is the key. The step size is the chunk size minus overlap token. That means each new chunk starts slightly before the end of previous chunk. This reduces the boundary loss, but overlap increases duplicated tokens, as we seen in the theory. That duplication increases cost because you store it, retrieve it, and then send it to the model. The rest of the function is doing exactly the same. Next is sentence-based chunking. For implementing sentence-based chunking, we have defined a small helper function. This just collapse new lines and split on the punctuation boundaries. So this is a function that implements sentence-based chunking. This function does token bounded chunking, but it respects the sentences. I start with empty buffer here and then keep adding the sentences until one or more would exceed the token limit. When the buffer would exceed max token limit, I omit the current chunk and start a new one. And this creates chunks that are usually more coherent because they end at sentence boundaries. Now we move to the structural chunking, which is structure-based chunking. This is extremely useful for docs and wikis. So what I'm doing is I'm splitting the document into lines, then build the section on headings that start with a hash. Each section becomes a chunk like heading, colon, body attached to it. If a section is too large for token budget, then I fall back to the dynamic sentence chunker, the function that we saw before this. So this is structured first, then token bounded chunking. Next is a semantic TF-IDF grouping. Now for semantic chunking, production system often use embeddings, but I want to keep this demo simple and dependency light. So I split the text into paragraphs and create TF-IDF vectors. And then I compute cosine similarities with this function. First we create TF-IDF vectors, then compute cosine similarities on that. So I can decide if two adjacent paragraphs are about the same topic or not. Then I merge the adjacent paragraphs only if the similarity is above a threshold. And then merge chunk still fits the token cap. This is not a very perfect semantic chunker, but it just gives you an idea how semantic chunker works. Next is LLM-based chunking. It's the most flexible approach. I'm gonna ask Groq Llama model to split this document into 4 to 6 coherent chunks. So I'm writing a prompt where I'm saying split the document into 4 to 6 coherent chunks for RAG retrieval, and I'm giving some strict instructions and requesting the JSON output only. The JSON output is important because it makes the result easy to parse reliably. And then I call Llama's client chat completion create function with the very low temperature to keep it consistent. And then I pass the JSON response and convert it into chunks with titles. So as I said, this method is powerful for messy sources like transcripts, but it's a bit more expensive and less deterministic than rule-based chunking. Then I have keyword score, top K chunk, and ask Groq with context. These are 3 tiny retrieval functions to make the output more clean. So the keyword score is intentionally to mimic how vector databases work. This is not vector database, but that's what it's gonna do. Top K chunks is also another function to sort the chunks by score and then return top 3. Then the next function is ask Groq with context. So this is to ask the model to answer using the provided context. In this case, we are giving strict instruction to the model that answer only using only the provided context. If missing, say what is missing, and then the user prompt. The constraint makes this demo more honest. Then a show function just to display helper function. So this function prints a strategy name, which is whether it's a fixed term chunking or whether it's a sentence based chunking. Then the number of chunks. Then a short preview of the very first chunk. Token and chunks. Then it also finally print the model's answer in the last case, which is LLM-based chunking. This keeps the output consistent across every strategy. So when I run this function, it's gonna call each function that we have seen above and print the output based on the question. So we are going to pass the same document to each type of chunking, and we are going to use the same model, but we are using different chunking strategies. And let's run this function and see how different chunking strategies produce different chunks and how useful they are. Let's run this function. Let's look at the output. So start with the fixed size chunking. You can see here that the document was split into 2 chunks and each around 110 tokens, because that's what the limit we defined. That's expected. And then the preview of the first chunk shows that it contains the RAG overview section, and then immediately it continues to the second section without considering the sentence or section boundary, which is also expected, as we expect the chunker to chunk based on the token size. It simply slices wherever the token limit is reached. Despite the random chunking, the model is still able to answer the question. Just to look at the question again, the question was, what are the trade-offs of the overlap in RAG chunking? It says overlap in RAG chunking repeats a tail of text into the next chunk to reduce boundary loss. However, it increases duplicated tokens, cost, and sometimes retrieval noise. So this highlights an important point, that fixed size chunking can work, especially for the simple documents like this or with the direct questions, but it relies on the model compensating for the imperfect context. Next, we look at the fixed size with overlap. The number of chunks still 2. The chunk size remains slightly or roughly the same, with 110. The difference is that we intentionally repeat a small portion of text from end of the one chunk into the beginning of the next. The effect of overlap is the retrieval score. It's 6.4 rather than 6.2. This indicates that the second chunk has become more relevant to the question because it contains overlapping context. The model answer is slightly more refined, which is overlap in RAG chunking repeats a tail of 2 text into next chunk to reduce boundary loss. However, this approach increases duplicated tokens, cost, and sometimes retrieval noise. So this demonstrates exactly why overlap exists. It improves the continuity across the chunks, but obviously at the expense of duplicated tokens and higher runtime cost than the fixed token. Now let's look at the sentence bounded chunking. We end up with 2 chunks again, but notice that the first chunk is now 92 rather than 110. That's because we no longer forcing the exact token count. Instead, we allow the chunks to end at sentence boundaries as long as they stay within the token budget. This small change has important effect. Each chunk now is semantically coherent because it contains complete sentences. You can see, and because we are only printing very first chunk, we can't see exactly how different the further chunks are, but we can look at the retrieve top 3 scores, which is 5.4, which are more balanced than the fixed size case. This tells us both chunks contribute meaningfully, equally and meaningfully to the question, to the response. Then we move to the structural heading first, chunking. Instead of 2 large chunks, in this case we have 5 smaller chunks, each aligned with the document sections such as RAG overview or overlap, etc. So we'll see the first chunk is only 32 tokens, and preview shows that it contains exactly one self-contained idea. It doesn't have anything further than that. Then when we look at the retrieval, we see 3 chunks contributing meaningfully with score 332. This indicates that the retriever is pulling multiple focused chunks, each addressing part of the question. Now look at the answer. The model answer reflects that instead of single sentence, it produces a structured explanation with clearly separated points, and which are the duplicated tokens, increased cost, and retrieval noise. This is a strong signal that clean and well-scoped context improves reasoning and the clarity, even when underlying model and the question remain the same. Next one is semantic TF-IDF similarity grouping. We again see 5 chunks here, and each around 30 to 35 tokens. These chunks are not based on the heading in this case, but on topical similarities, on the cosine similarity, which means grouping sentences that talk about the same idea. The retrieval score here is 332, again same as the structural chunking. This suggests that semantic chunking is also effective at isolating relevant concepts. The model answers is concise in this case, and accurate obviously, and covering the same trade-offs of the overlap. While the final wording is similar to earlier strategies, the key difference is how clean the retrieved context is. Now, the semantic chunking is particularly useful when documents lack clear structure, but it does require additional pre-processing and computation. Then comes the LLM-based chunking. This is the final one. Once again we end up with 5 chunks, and each focused on single idea and roughly the same size as structural and semantic chunks. The first chunk previews here shows a clear title, which is RAG overview, and a self-contained explanation, which is exactly what we asked the model to produce. The retrieval score is 332 again, indicating that multiple focused chunks contributed to the answer. The model's final answer is accurate and well balanced. While it doesn't introduce new information, it benefits from having context that's already organized in a way that aligns with the reasoning. This approach is powerful for messy or unstructured data. So the overall takeaway is that across all strategies, the model is capable of answering the question correctly in this case, but the path it takes to get there, the quality, the structure, the clarity of the context changes significantly depending upon how we chunk that data. Fixed type chunking is easy and cheap, but it places more burden on model to restructure meaning. The structural, semantic, and LLM-based chunking provide cleaner context, which often leads to clearer and more structured answers. This is why chunking is not just pre-processing detail, it directly shapes the context window at runtime, and that context shape how well the model can reason. And that's it for now. If you found this breakdown useful, please like the video and subscribe to the channel. I'll see you in the next video in the RAG series.